Hello, midnight coders. Come on in, grab a seat, grab a seat. You know what I think is one of the weirdest experiences in learning software development? You can spend months learning Java. You learn variables, loops, classes, inheritance, interfaces, and then maybe you've even built a Spring Boot application. And then somebody puts a problem in front of you and says, okay, solve this. And then suddenly you're staring at your screen and have absolutely no idea what to do. And that's where data structures and algorithms comes in. Because now I don't think that you're a bad programmer, you're bad at programming. I don't think that you're bad at Java, and I don't think that the answer is to memorize another 50 algorithms. Instead, I think there's a different skill that actually needs to be built. And that's where we are going to talk about today. So, welcome back to the Midnight Cafe. Make sure you've got your coffee ordered because we're going to be diving into DSA or data structures and algorithms on our just to expand on our Java roadmap and go just a little bit deeper. So, let's start with the simplest definitions. Data structures and algorithms. Two things: how to organize information and how to operate on that information. That's it. A data structure is a way to organize data. An algorithm is a way to process for solving a problem. And the interesting part is those two things are connected because the way you organize your data affects the way that you can efficiently work with it. And let's say that I have 100,000 orders in the Midnight Cafe and I want to answer a very simple question. What order is the most recent? Well, how do I store these orders? Is there already orders from, are these already ordered from oldest to newest? That's one problem. If you're sitting in some arbitrary collection, that's another. If I need to repeatedly find a customer by ID, that's another problem entirely. So DSA isn't just exactly here's a linked list or here's a binary search. It's really about asking what information do I have, what do I need to do with it, and how much work will that take? That, that last question is the sort of thing that starts getting really interesting. Because you probably heard of Big O, and you've probably, let's say, you're if you're anything like I was when I first encountered it, somebody probably wrote down an O of n or O of log n or O of n squared on a whiteboard and then immediately started talking about mathematical foundations and functions, and you're sitting there thinking, cool, but what does that actually mean when I'm writing Java? Like what? So let's forget this fancy notation for a second and let's talk about the work. Imagine I have one coffee order. I look at it, done, easy. Does the number of orders affect how long it took me to look at a particular task? No, that's constant time. We call that O of 1. One operation, whether I have 10 orders, 1,000 orders, or a billion orders. The operation itself doesn't grow with a size. That is O of 1. Now let's say that I have a pile of orders and I'm looking for one particular order. I might have to inspect every single order. 10 orders, maybe 10 checks. 100 orders, that's maybe 100. 1,000, that's potentially 10,000. So the amount of work grows with the amount of data. That is O of n, or linear time. Now, Here's where it gets interesting. Imagine our orders are sorted and I want to find a particular order. I don't necessarily need to look at every single one. I can just simply look in the middle, and if the one that I'm looking for is smaller, I can throw away half of the search. If it's larger, I throw away the other half. And I keep doing this half and half and half, and this is what we call O of log n. It allows us to cut the problem up into smaller logs. Like you can imagine trying to bring trees into your house for firewood. You don't take the whole tree, you chop it up into logs so it's more manageable. Log of O of log n allows you to throw away big chunks going from a million to 500,000, 250, 125, and so forth. And this is why algorithms like binary search are so powerful. We're not just searching, we're eliminating possibilities. So now let's make this a little bit uglier. So suppose I have to compare every single item with every other item, and for every other item I inspect all of the other orders. So n times n, which gives us O of n squared, quadratic time. And you can see why this gets expensive very quickly. 10 items, 100 comparisons. 100 items, 10,000. 1,000, that's 1 million. And that is important part. Big O is not just about saying O of n squared is evil. O of 1 is perfect. It's about understanding how the amount of work changes as the input grows. And there's one more complexity that we need to talk about, which is O of n log n. And you see you see this a lot in an efficiency sorting algorithm. Conceptually, you think of something like divide the problem and then do the work across the divisions. And it's more expensive than linear time, but dramatically better than quadratic time as n gets large. So in the complexity categories, I want you to keep in your mental toolbox that there is O of 1, which is constant, O of log n, which is logrammatic, O of n, which is linear, O of n log n, which is linearithic, and then O of n squared, which is quadratic. And don't memorize these um, because somebody told you to. Start asking the question instead, how does the amount of work change as the input gets bigger? That is where the beginning of algorithmic thinking takes part. So now, let's say that, let's talk about data structures for a moment, because there's another mistake that I see all the time, and that is people treat data structures like vocabulary words. Array, linked list, stack, queue, deck, tree, graph, hash map. Memorize the definitions, move on. But that's not really useful. I want you to think of every data structure as a decision. You are deciding how your data should be organized, and the decision that changes what operations are easy and what operations are expensive. So, for example, let's start something simple with an array. If we have an array like this, then if I was to say, okay, give me the index of 3, I can jump directly there. It doesn't matter that I have a lot of entries. That's the idea behind constant time access. I know exactly where the thing is. And now let's imagine a stack, something like this, where you put things on the top and you take things from the top. Last in, first out. LIFO. This is useful because the operations themselves have meaning. Now, on a queue, you may have something that looks like this, and it's first in, first out, or FIFO. Now, again, you're choosing a structure based on the operations your problem needs. And in Java 25, this gives us a really nice way to talk about ordered collections. Sequenced collection. So instead of instead of having complex, completely different vocabularies depending on which concrete collection that you're actually dealing with, this gives us something like get first, get last, add last, remove last. And then it simply just looks like this. And that is useful. But there's something that I want to emphasize. The API is not the lesson. The lesson is what operations does my problem need? Now, Java gives us a clean way to express this answer. This is where DSA starts getting uncomfortable for a lot of people because when an array feels simple, you have ABC, um, you can see the values, but that now there's a blind, but now let's build a linked structure so that you have A at the front, points to B, points to C, points to null. And now the important question is, where's element number 2? Well, what does the node point to? And then we start changing everything. So suppose I want to insert a new node. So I've got something that looks like this, ABC, and now I want to stick in X. So that's actually happening, or what's actually happening here. So we're changing references. We're not magically moving a bunch of values around, and we're not changing the structure of we're not changing the structure that connects the values, and this is one of the biggest conceptual jumps in DSA, is that you need to be able to look at ABC and mentally understand that A points to B, B points to C, C points to null. And that's the mental model. Once you understand references, linked lists become less mysterious. And eventually, trees and graphs start to also make sense too, because they're all built around relationships between pieces of data. Now we walk directly into another wall, recursion. So you write a method that calls itself, and the first response from people is, well, why would I do that to myself? Fair question, fair question. But recursion isn't magic. It's the idea that you can solve a problem by solving a smaller version of the same problem, and you need two things, a base case and a recursive case. So something that says we're done and something else that says let's solve a smaller version. For example, something like this, solve problem, if the problem is small enough, stop, otherwise continue working. That is recursion. And that is now, and now watch what happens when we build a little tree. So we have something that looks like this. And the tree is naturally recursive. The tree contains smaller types, so recursive algorithms become a little bit more natural way to work with these. And you can traverse a tree like such, and suddenly concepts like depth first search, tree reversal, binary search trees start making more sense. And not because you memorized a method, but because you actually understood the structure. And this is where Java 25 becomes really useful because we're not just here to show off the newest Java features. We're not. Um, we're here because the language should help us express the concepts that we're learning. For example, records give us a very clean way to model data, and pattern matching lets us inspect structures without burying the actual logic in ceremony. So conceptually, something like so. Now, look at what we are actually seeing. The tree structure, not 50 lines of setup code, not boilerplate, not structure, not algorithm, just the idea. And that's what I want modern Java to do for us is get out of the way. Java 25's compact source file model makes this even easier for small algorithm demonstrations because I can just write void main and then throw in some code and get immediately to the problem. That is the important that's important when you're learning because the goal isn't to memorize Java ceremonies just like we used to. Um, we can get the algorithm. The goal is to understand the algorithm. So now that we're now that we're getting on to the part I really want to talk about and take away from this video, because eventually you're going to encounter a problem that you've never seen before. And that's when you're going to be thinking, oh, I don't know this algorithm. And that's okay. You aren't supposed to know every single possible problem. Instead, you have to ask yourself a couple questions. What data do I have? What operations do I need? Is the data ordered? Do I need fast lookup? Do I need to process things in sequence? Can I eliminate half of the possibilities? Am I repeatedly looking at overlapping portions of the data? Do I need to remember previous results? Is the problem recursive? Does the data naturally form a tree? And are the relationships between arbitrary nodes? So these are the kind of questions that start revealing patterns. And let's talk a little bit about a sliding window. So you don't need to memorize some magical incarnation just to think about what you're doing. Okay? So you've got an array 1 through 7, and you're looking at a slice of it. So maybe you're looking at 1, 2, 3, and then you move. You're looking at 2, 3, 4, and then you move, and you're looking at 3, 4, 5, and etc. Um, you're maintaining a window over all of the data that's the concept. The implementation comes later. The idea with binary search is that the pattern is, can I eliminate half of the remaining possibilities? If yes, maybe you're looking at a logarithmic solution. Is there 2 pointers? Maybe you can process from both ends, and maybe you're scanning the entire structure. Is there prefix sums? Maybe you can do some work once and then the result, and store the result and reuse it later. Dynamic programming? Maybe you're solving the same problems um, repetitively or repeatedly, and you can remember those results instead of calculating them again. The point isn't memorize 12 named techniques. The point is to learn to recognize what the problem is that you're trying to maintain, eliminate, traverse, or reuse. And that is algorithmic thinking. So, the Midnight Cafe DSA workflow. Here's the workflow that I want you to use. When I give you a DSA problem, don't immediately start typing code. Okay? Step one, understand the data. What do we actually have? Numbers, strings, objects, relationships, ordered data. Step two, understand the operation. What are we trying to do? Search, insert, delete, sort, traverse, count, find a minimum, find a maximum. Step three, think about constraints. How much data should there be? Because O of n squared solution might be perfectly fine for 10 items and absolutely terrible for 10 million. Step 4, choose the data structure. Which structure makes the operations that we need efficient? Step 5, choosing the algorithm. Now, only now should you start thinking about the actual implementation. And then finally, analyze the complexity. What is the time complexity? What is the space complexity? And what happens as the input grows? This brings us back to our cafe. So imagine we have 100,000 orders, and every order has an order ID, customer ID, timestamp, items, and total. Now, I ask you, find the most recent order from a customer. Don't write the code, not yet. Think. What data do you have? Orders. What do you need? A customer's latest order. What operation matters? Lookup. What does the data look like? Does the order list have a useful ordering? Do we have some way to quickly identify a customer? Suddenly, we're not looking at a blank screen anymore. We're asking questions, and these questions guide the solution. That is DSA. And this is what I want you to walk away with, okay? After these lessons, I don't want you to be thinking, I need to memorize more algorithms. No, 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 no. What you should be thinking is, I need to get better at understanding the problem. Because once you understand the problem, the data structure starts becoming a decision, and the algorithm starts becoming a decision as well. And big O becomes a way of measuring whether that decision is going to survive when the data grows. And yes, we are doing all of this with modern Java, Java 25 and beyond. Not because Java is a modern language, but because 25 plus has modernized the painful language that we all love to hate. And we're going to use modern language features where they make the biggest clear, where they make the ideas clearest. So compact source files, records, pattern matching, modern collection APIs, and everything else that Java gives us. But I'm going to keep making one distinction throughout this entire roadmap. Java is a tool, DSA is a subject. Because I don't want you leaving here knowing 5 cool APIs. I still want you knowing how to solve a problem. I want you to understand what or why you would choose one structure over another, and why one algorithm scales and others don't. Why O of n can beat O of n squared by an absurd amount of time as the input grows. Why binary search can eliminate 500,000 possibilities with just a handful of decisions. And why references matter, why recursion works, and of course, why trees and graphs are just different ways of representing relationships. And most importantly, how to look at a problem that you've never seen before and start breaking it down. So here's your challenge. I'm going to give you a clear problem. The Midnight Cafe has 100,000 orders. Each order belongs to a customer. A customer can place many orders, and I want you to be able to quickly answer me, what was the customer's most recent order? I don't want you to write the code yet. I just want you to answer 5 questions. What is the data? What operation matters? What constraints do I have? What data structure should help? And what is the expected complexity? After that's the beginning of DSA. Not memorizing a problem, not blindly typing code, but thinking. And that's really what I want to teach you. Because you're not learning DSA just so that we can pass a technical interview. We're learning it because software is fundamentally about working with data, solving problems, and making decisions about how work gets done. And once you understand that, the syntax becomes the easy part. Java gives us some beautiful tools to express these ideas cleanly, but the real skill is learning how to see the problem. So finish your coffee. Take that problem apart. Keep your curiosity open, your skills sharp, that coffee cup full, and I'll catch you in the next meetup.